In this video, we're going to talk about running experiments on computers using a method called simulation. The simulation refers to any method that imitates a real-world process or a real-world system. Why do we want to build computer models of these things? Well, uh, often in real life, experiments on some systems can be very expensive. Um, Sometimes they're not even feasible to do, right? If you were an economist and you wanted to study how recessions take place, right, it would be infeasible and also unethical to try and put multiple countries into recession just for the purposes of an experiment. But we can create computer simulations of economies to try and model what might happen. It also allows us to conduct experiments that in real life might take a very, very long time to happen. We can also compare different examples. We can even try and do simulations of things that are almost impossible to get to occur in real life. Now, there's a big caveat to using simulations rather than real life experiments, which is that simulations, of course, are all wrong. Inherently, they're simplified models of real life, which means they don't capture the full complexity of what goes on in the real world. There's a famous saying, which is usually attributed to a statistician called George Box, that all models are wrong, but some are useful, right? In other words, that uh, we can't completely trust what a simulation tells us, but we can sometimes get useful insights out of it. So where might we use simulations to generate useful insights? Well, one example is weather forecasts. A lot of weather forecasts work by running simulations of what's going to happen to the weather in the future. And they then convert these into the forecasts that you get when you're trying to figure out how many layers of clothes to wear for the day. Another use is in engineering when engineers are trying to figure out the structural integrity of structures. If you're trying to build a bridge, for example, you could create a computational model of the bridge and study how it behaves under different forces and loads. We can also try and model human behavior with simulations. This is an alternative to try to doing experiments with actual humans, which are sometimes prohibitive, especially if it involves getting humans to do things that are might be considered unethical or dangerous. So there are lots of different types of simulations, right? Different ways that we can try and model reality on a computer. There's not one system of classification, but there are a few common types that it's useful to know about. So Monte Carlo simulations refers to a computer simulation that repeats an experiment over and over again, where there's some randomness in the experiment. And then you look at the range of outcomes. For example, right, if you wanted to look at the outcomes of flipping a coin, well, that's random, right? Sometimes it's going to be heads, sometimes it's going to be tails. You could do it over and over again and look at the distribution of heads and tails, right? What percentage of the flips come up heads, what percentage come up tails, and that might allow you to figure out whether the coin is seems to be fair or not. Another category of model are called systems dynamics models. In these, we tend to model parts of the system as compartments or buckets, and then allow quantities to flow between those buckets. An alternative to that is something called agent-based models, where instead of modeling sort of compartments of or buckets of things that are considered interchangeable, you instead try to model the individual things. So you would create individuals, which often represent humans, in your models on the computer, and you would allow those computational humans to then interact with each other and study the behavior that results. Some of these simulations involve adding in space and allowing things to move around in 1, 2, or 3 dimensions, and seeing how they spread out across that space. And there's lots of other variations on these types of models, and nuances and other categorizations. So we talked about flipping a coin as an example of a Monte Carlo simulation, and here is how you might implement that in R. So we're going to use this function called sample, which randomly picks values from another vector. So if we have a vector called coin, which we define here on line 1, that has 2 values, heads and tails. On the next line of code, we can then call the sample function, and the first argument we're going to pass is that coin vector of heads and tails. The second argument is then the number of times that we want to randomly pick a value from the coin vector. So we're going to pick randomly from the coin vector 10 times, which in our simulation is going to be equivalent to flipping the coin 10 times. We also, in this case, need to specify another argument called replace, and we're going to pass the value true to that to indicate that we want to be able to pick these values over and over again. Right? In other words, if you get heads the first time, you're essentially going to replace heads back into the pool of values you could pick from. Okay, so you can pick heads again the second time. And then what happens when we run this is we get a vector of 10 outcomes, right? Each one responding to either heads or tails, depending on what the sample function randomly picked for us from the coin vector in each one of the 10 random samples. So this is what the function signature of the sample function looks like. As we talked about, the first argument is a vector, here represented by the argument x of the values we can pick. The second argument is the size, right? The number of times we want to sample from the vector x. We have to specify whether we want to replace the values from x or not. The default is you don't replace them, which is why here we had to specify that we did want to replace them. And finally, you can also optionally provide probabilities of picking the different values from the coin vector. Right? If you don't specify this, then each value of the coin vector is treated as equally likely to be picked. Right? In other words, 50% of the time we'll get heads, 50% of the time we'll get tails. But if you wanted to simulate an unfair coin, then you could specify different probabilities. So for example, if we wanted a really biased coin, where maybe the probability of heads is 90%, and we get tails the remaining 10% of the time, then we could specify this vector which we pass to the prob argument, where we specify 2 probabilities which will be matched up with the 2 values in the coin vector. And we can see when we then sample again, in this example, we've got heads all 10 times. So obviously, there are many different ways that we could write a simulation. But in general, simulations all tend to involve some core components, no matter how we implement them. So typically, we'll have some initial conditions. Where do we start when the simulation starts? We'll also have rules for how the system evolves. So in the coin flipping example, right, the rule is that the coin gets flipped. Then there can be random elements. There's not mandatory that there's randomness in your model, but if you want to get a different result each time, which is typically what happens in real life, then you need to incorporate randomness. A lot of models also implement time to some extent, right? So in our coin flipping example, each flip presumably happened later on in time, right? We weren't flipping 10 coins completely simultaneously. We were flipping the same coin over and over again. And finally, right, presumably every simulation involves you trying to measure something, right? The quantity that you're interested in, the reason that you're creating the simulation in the first place. So here's a system dynamics example, right? System dynamics models, if you remember, were where we had categories of things, and then we allow quantities to flow between those categories. So here we're simulating a bank balance, right? So we've got a category that is the balance of a bank account, right? In this case, it's 100 somethings, right? Maybe $100. And then we also have an interest rate, 5% interest rate here, 0.05. And then we have a simulation that's a for loop, and we're going to iterate through 10 years. Okay. And in each one of those years, we're going to calculate the amount of interest that our bank balance earns, right, by multiplying the existing balance by the interest rate. Then we're going to update the value of our bank balance by adding that calculated interest to the existing balance. And then finally, we're going to print out the value of our balance at the end of that year. And then we're going to repeat that 10 times in total. Okay, and you can see the results here, right? At the end of year one, we started with $100. We started with $100. We added $5 of interest, right, from the 5% interest rate, for a total of $105 at the end of the year. Okay, and as we go through our years, right, the amount of interest we earn each year increases steadily. Right, by the last year, we're actually earning $8 in interest rather than the 5 that we started out with. So the starting conditions here, right, are that the bank balance is $100. The rules, right, are that the bank account increases each year by the amount of interest that's been paid. The time here is pretty explicit because we're iterating through 10 years. There's no randomness in this model. Right? It's predefined basically what's going to happen. If we were to run this code chunk all over again, we'd get the exact same result. We could add randomness in, right? We could allow interest rate to vary each year randomly, but that would be a more complicated model. And finally, of course, we have the thing that we're actually interested in measuring, which is the value of the bank balance after each year. We previously mentioned this quote that all models are wrong, but some are useful. So you might well ask, well, okay, how do I know when my model is useful or when it's so wrong that I can't get any useful information out of it? Well, this is where a process called verification and validation comes in. Verification is a step where we can check that the simulation is implemented correctly. For computer models, this typically involves checking our code to make sure that we have no bugs and that the code is doing what we intended it to do. Validation is a more complicated step where we actually ask ourselves, how well does the simulation match up to reality? So are the assumptions of the model realistic, right? And then after we've run the model, are the results that we get, do they match the values that we might also measure in real life from similar scenarios? By doing these two steps, we can figure out ways to improve our model, as well as getting an idea of how well it matches reality and in what particular scenarios it might give us useful insights.